Have you ever really thought about how manufacturers join totally different metals? I mean, things like lightweight aluminum to super strong steel. It's a huge deal in everything from the car you drive to the spacecraft flying overhead. But hidden deep inside that weld at a microscopic level, there's this risky chemical reaction that can literally make or break the entire structure. So let's dive in and see how engineers are taming this tiny, tiny beast.
Right, so how do you actually do it? It's definitely not as simple as just melting two metals together and hoping for the best. When you try to join materials like, say, aluminum and copper or titanium and steel, you're basically forcing elements that really don't want to mix to form a permanent bond. And getting that bond just right, well, that's a massive engineering puzzle.
And to solve that puzzle, we've got to look at the weld on a microscopic level. We need to find the unseen bridge that's actually holding the whole thing together.
So when you weld two different metals, the atoms right at that boundary, they don't just mix, they actually react. They form totally new, distinct chemical compounds. And these are called intermetallic compounds, or IMCs for short. Think of it less like mixing two colors of paint together and more like a chemical reaction that creates a brand new substance. This new stuff, this is the microscopic glue, the metallurgical bond that connects the two metals.
But here's the catch, and it is a big one. This essential bridge, this glue that you absolutely have to have for the weld to even exist, it's also the source of its biggest potential weakness. It's a classic double-edged sword.
And here you can really see the two faces of these IMCs. On one hand, a thin, continuous layer is exactly what you want. It's the foundation of a strong bond. But if that layer grows too thick while you're welding, it becomes incredibly brittle. Seriously, think of it like a tiny layer of glass sandwiched between two pieces of steel. Instead of making it stronger, it becomes the perfect starting point for cracks, which just kills the toughness of the joint.
And hey, don't just take my word for it. The research totally backs this up. As Young and his team pointed out, when you pull these welded joints apart, they almost always break right at that brittle IMC layer. It's basically the weld's built-in Achilles heel.
Now, this isn't just a weird quirk with one or two specific metals. Oh no. This challenge of brittle IMCs pops up all over the place, across a whole range of really important industrial materials.
Just take a look here. Whether we're talking about electronics with aluminum and copper, or aerospace parts with titanium and steel, each unique pair creates its own set of these problematic compounds. The chemical names might be a mouthful, but they all share one thing in common. If they grow too thick, they wreck the integrity of the weld.
Okay, so the problem's pretty clear. The very thing you need for the bond is also a potential point of catastrophic failure. So how do engineers get around this? Well, this is where the magic happens. They've developed a whole toolkit of really clever solutions to get this process under control.
And this right here is the crucial point. Engineers aren't trying to get rid of the intermetallic compounds. They can't. They're essential for the bond itself. The real goal, the name of the game, is to control them. It's all about keeping that IMC layer as thin, uniform, and well-behaved as possible. You've got to tame the beast, not try to destroy it.
And how do they pull that off? They've got a whole bag of tricks. We're talking everything from using high-frequency vibrations and super precisely controlled laser beams to adding these thin interlayer metals that act like a buffer between the two main materials. Let's check out a couple of these in action.
First up is a really cool technique, adding high-frequency, ultrasonic vibrations while the welding is happening. It's kind of like shaking the atoms into just the right place.
And the results? Whoa, they're pretty impressive. For a really tricky weld between aluminum and titanium, one study found that adding these vibrations increased the joint strength by a massive 43%.
This chart basically shows you how much force it takes to break the weld. And you can see the ultrasonic-assisted weld can handle way more force before it fails. And it's all because those vibrations helped break up the big, clunky IMC crystals, creating a much thinner, more refined bond.
Okay, so that's one way to do it. But another really clever strategy is to just change the chemistry right at the interface by adding a third material, like a super thin coating.
And the impact here can be absolutely staggering. In copper-aluminum welds, which you see all the time in electronics, adding an optimized nickel coating boosted the shear strength by over 200%. That is huge! The nickel basically acts as a barrier, and it stops those brittle copper-aluminum IMCs from growing out of control.
All right, but what if you don't add anything new, and instead just get way smarter about how you apply the heat? Well, that's where really cool techniques like laser oscillation come into play.
So instead of just a straight-line laser beam, this technique rapidly oscillates or wobbles the laser. A standard weld often creates this thick, messy, and weak two-layer structure of IMCs, but the oscillating laser actually stirs the molten metal, breaking up those brittle compounds and helping form a single, thin, uniform layer. We're talking just 1.4 micrometers thick. I mean, that is an insane level of precision and control. And the result of all that laser wobbling on an aluminum to steel joint? A 65% jump in tensile strength. It's just another awesome example of how controlling the process on a micro level gives you these huge benefits in performance.
So what does all of this microscopic engineering really add up to in the real world? Well, it transforms a fundamental problem from something brittle into something truly brilliant.
Look, the reason this matters is pretty simple. Mastering intermetallic compounds is what lets us build the things that define modern tech. It's what makes lighter cars possible by joining aluminum and steel. It gives us more reliable electronics with copper and aluminum, and cutting-edge aerospace parts using titanium. At the end of the day, it's the key to making everything stronger, lighter, and more efficient.
So if there's one thing to take away, it's this. So much of engineering is about turning a bug into a feature. By understanding and precisely controlling what seems like a fundamental weakness, this formation of brittle compounds, engineers can actually transform it into a predictable, reliable strength. And that is how you build the future. It's just a powerful reminder that mastering the challenges at the smallest possible scales is what makes the biggest innovations possible. It kind of leaves you wondering, right? What's the next nearly invisible, microscopic problem that, once we solve it, is going to unlock the next generation of technology?